Let me talk about categories of polymorphism, particularly coercing polymorphism, overloading polymorphism, inclusion polymorphism, and parametric polymorphism. First, let me talk coercing. Coercing is the process of converting a data item from one type to another type without explicit casting or using explicit conversion syntax. In other words, it is a process of converting a data item from one type to another type implicitly. Let me talk this through coding. First, I have a double variable du x initialize to 3.3, and I create integer variable and set it to x. So here what happens is this x is a double type variable which has a 8 byte memory space, and y is integer 4 byte memory space. So you have to shrink the amount of memory space, and also what happens is this data is stored in that memory space in a totally different way than the way it would be stored in the integer type. So it will actually take the data and truncate this fractional part, and then convert this into the binary conversion binary bit form, and then copy that bit into the memory space. That is what happens here. So but it happens automatically, therefore we call this as implicit casting, and this is also called as coercion. We can make use of this coercion to make a function to get executed for different data types. So for that, let me create a function called sum, which has a double parameter and second double parameter, and it returns the summation of a and b, and we have a return type double. Now for this function, we can obviously call this function with double argument values like 3.3 and 2.2. This should be obvious, but we also can call this function with other types, integer type, let's say 5 and 6. So same thing that happened in this assignment, that happens when you are calling this function. So this integer value is actually being assigned to a. So in that process, this integer is converted into double type data, and then it is actually used. That double value is used here in the computation, and the result is returned. But this also happens automatically. So now we have a situation where the same function called sum can perform its execution or show its behavior for different context. When I say context means the set of this type of this arguments passed. Therefore this behavior is called polymorphism, and especially coercion polymorphism. And this coercive polymorphism allows a function to work with arguments of different data types implicitly. As you can see, it happens automatically. Manual conversion is a type to a type is not needed. Now let us start talking about overloading polymorphism, another category of polymorphism. To explain overloading polymorphism, I am going to be creating two overloaded version of a function. Name is r equal. It will actually do the comparison and return a boolean type data. So therefore we have return type boolean. It will return true or false. So it will receive a double first parameter, double second parameter, and it will compare and return true if they are same. Before that, let me create another version of this function, overloaded version for integer type, and I'll just return if a equals to B, true, otherwise return false. Right, we have this sort of logic here, but in the case of double it's a little bit tricky, because in the case of double, two values can be, let's say, 2 point, so for example, if you have 1.9999 and then 2.00001, if you have these two values, then you in many situations you can assume that these are equal. But if we do use the same logic of comparison, it will not work. They will be different. So you need to use a little bit different approach here. So the approach you will be using is, you actually see the difference between, absolute difference between these two parameter values, and if they are actually smaller than a very small value, then you can consider these two values are equal. So we can do something like this. If ABS A minus B, this will compute the absolute value of the difference. If this is less than, let's say, 0.001, then we consider it is equal. So return true, otherwise return false. So now the logic is they are implemented differently. They are same function, different parameter, but their logic is different. Now with this, we can create a few lines of code here to use it. Let me have cout statement are equal, and then let's say 1.9999 2.001. And also sorry, 5 and 6. So these are two invocation of this this function, and this invocation obviously will go for this function, or the compiler should actually bind this invocation to this function, and the compiler should bind this function invocation to actually this function, the second version of the function. Now this is we have the function with the same name implemented, so that it actually behaves differently for different parameter types. So that's why this is called the overloading polymorphism. When we have multiple functions with the same name, but with different parameter types, or different number of parameters, or different order of the parameter types. For example, if I have an integer double, and first parameter integer, second double, and I have another function with first parameter double and second integer, and then they are also the overloaded version of this function. So, and then the functions are implemented differently. Then we have a situation where the overloaded versions of the functions behave differently in different contexts. When I say context, it is the parameters arguments with his type of the arguments with his the functions are actually invoked. Now it is time to talk about inclusion polymorphism. This is a runtime polymorphism, which means polymorphic behavior of a function is determined at runtime, not at compile time. This polymorphism relies on inheritance and virtual functions. Let's learn it more through coding. To talk inclusion polymorphism, I need to have a hierarchy inheritance, the classes in inheritance relationship or hierarchy of classes. So let me create a class called animal, and I don't want to have the data members here, only the one function make sound. So always don't forget to put a semicolon at the end of class definition. I want to create another class, dog, publicly derived from animal, and with the same function but implemented differently. In this case, I think it will dog growl, barks. And I have another class, cat, and cat does meow. And I want to have another class which would be derived from this dog class. So in that case, dog will be the base class and that new class will be the derived class. So maybe pet dog. Suppose this pet dog does winning more than barking. So we have this hierarchy of classes. On the top level were animal, and it has two children, dog and cat, and dog has one children, pet dog. So with this hierarchy, we can actually implement a polymorphism through pointer. First we create the base class pointer, call it aptr. It's always safe idea to initialize it to null ptr when you create a pointer. Then I can use this pointer to point to animal object. And since we have this make sound function, so we can call this make sound through that pointer. And after a while I want to use this pointer to point to dog class, but you want to make sure that when you are reusing this pointer to point to new dog like this, then it will be detached from this dynamic object in dynamic memory space, which will be not released. Then this memory space will be occupied and will not be usable. So that is called a memory leak. So if to avoid memory leak, you properly release it, delete, and then allocate it again, and call make sound through this, and again, and make it point to another object, new object is cat, and then again delete, pet dog. So we have these things here. Now at this point, if you are familiar with the dynamic polymorphism or dynamic object, this dynamic object has always two types: static type. Static type is the pointer, type of the pointer animal, and it has a dynamic type. So dynamic type is not defined at this point, but when you set it to this animal, then at this point the dynamic type becomes animal. At this point the dynamic type becomes dog. At this point the dynamic type switches to cat and pet dog. So dynamic type keeps changing, but static type does not change. It remains same. Now what I expect here is, since it is pointing to this animal object, so this invocation will actually be this will display some logic. Call a function, that means it will behave its behavior. I expect its behavior would be a certain way. Would be the behavior actually defined by by animal class function, right? And in this case, in the second case, I would expect the behavior to be defined by dog class make sound function. In this case, I expect its behavior actually is defined by cat class make sound function, and in this case its behavior is defined by pet dog classes make sound function. So it is the same thing. I mean, if you look into this, this is I mean, the syntax of invocation is same in all cases, but their behavior should be different based on the context. That means context is the dynamic object the pointer is pointing to, or the dynamic type of that polymorphic object. So in this case, in the first case, I expect this text displayed. In the second case, I would expect this text displayed. In the third case, I would expect this text displayed. In the fourth case, this text is displayed. So let us switch to the terminal and see whether we can see that expected output. So I will actually compile it and execute. It is displaying this text, animal sound. In all the four cases, the same thing has been displayed. That means it is not actually behaving the way we wanted. The behavior is not different, it is behavior is same, right? So behavior of this invocation is same because they are displaying the same thing. That means they are actually calling this function. That means we don't have a polymorphic behavior in this case. This is not a polymorphic behavior. So to enable the polymorphic behavior, this make sound function must be a virtual function. So you can make this function virtual by putting the keyword virtual here in the beginning. Now this will actually turn this function virtual, and which actually enables polymorphic behavior of this function. So let us see. This is a warning. I'm going to be ignored because this is in particular case there is no this is inconsequential. So let me execute it. So now you can see in the first case animal sound is displayed, in the second case bark, and then mew and whinnying. So that function actually is behaving differently in different contexts in this case. So this is our polymorphic behavior. Right. So the complaint was that it was asking me to have a virtual destructor here. So I think this will actually remove that complaint. But I'm not going to explain this further because our focus is in this is not a focus. If you're interested to learn more, I have a recording about this topic in one of the previous videos. I encourage you to watch. I think this is all about inclusion polymorphism. Now it is time to talk about parametric polymorphism. It is a kind of polymorphism where a function or class assumes different forms based on the type of the data to be used with them. Template is a tool to realize parametric polymorphism, and you will also see the term generic polymorphism used for this. Let us learn this through coding. In this case, my assumption is that you are familiar with template syntax, how they are created, how they are used. If you are not familiar, I encourage you to go and watch my previous recording on templates. Here the purpose is to explain how this template is a polymorphism. So I am going to create a template function here. This is called a generic type or t is called type parameter, and I want this function to return a value and take two values in its two parameters. I have a sum initialized to 0, sum plus equals to, just I want to actually expand this. This could be, everything could be put in a single line, but I just want to make it look a little bit bigger size. So this t is this generic type, and we have two parameters. These are also called as type parameters. Now this is a template function which receives two data items, and it does the sum. It computes the summation of those two and returns the result, the summation result. Now in the main function, let me create some data to be used when calling this function. I have integer data 5, b equals to 6, and I want to have another variable where I will store the result of computation or the data that is written by something like this. So c equals to, I will have sum a and b, and I have double d equals to 5.1, e equals to 9.2, and f to store the result. F equals to sum d e f, sorry, d and e, and I have float g equals to 2.2 f, h equals to 8.8 f, and I equals to sum g and h. And I also want to use string j equals to hello, and k equals to, one space character. This is not a character, this is a string. It consists of one space character followed by null terminated characters, the total 2 characters in this string. L equals to volt, and m new variable to store the result. So I have m equals to sum j and k, and m equals to sum m and l. So in this case, I will not run and display. If you are interested, you can type this code and try executing it. From my perspective, or my assumption is that there is no syntactic problem here. It will run well. What will happen here is when the compiler sees this summation, this expression, we can call this as an expression, then it will actually go ahead and pick this function and create a version of this function for integer type, because the type of the arguments is integer. So it will create a function something like this. So the compiler will actually do this, and when the compiler says this expression, it will go ahead and it will create this function, and it will actually link this invocation to this function. And in this case, compiler will create another version of the function for double type, something like this. So now we have another version of the same function created for double type, and in this case, compiler will create another function for floating point type, and when compiler sees this expression, it will look into the type of the arguments, which is string, so it will create the same function for string type. So we have one function assuming different forms here. These are the functions that would be you don't need to I don't need to create, programmer doesn't need to create this, compiler will do this itself. But if you see this this is the function, template function, assuming different forms based on the type of the arguments or data used with these functions. So in that sense, this is actually exhibiting, displaying a polymorphic behavior. Right, let me comment this out. So again, let me explain it. The display of the polymorphic behavior happens actually at compile time, because compiler does all these things, and compiler determines the behavior of the template function for the function calls based on the type of the data used with function call in these statements. So this is a polymorphic behavior. This can also be seen for the class. If I want to convert this sum function as a class, then what I can do is do something like this. You need to have this line in the beginning, and then class name. Let me use this sum with uppercase character S for class name, put everything inside, and I don't need any private data, public, and we have just let me change the name. You can have this name because this lowercase, this is uppercase, but I just want to change it so that there could be less confusion. So let me call this run. So we have this member function, and then to use this class, what we can do here is you need to create an object, and you cannot use this directly like this. This is not a function. Function object is a different concept that I'm not going to talk. That is a little bit more advanced concept. So first you need to create an object of sum, maybe S1 or S2, S3, S4, and you can use this like this, S1 dot run. But you need to specify, because this is a template function. If you have watched the template video, then you realize that the way you use this create a object is you need to actually tell compiler for what type you want to create this object for. So in this case, S1 I want to create for integer type, S2 I want to create for double type, I want to, let me just make correction, DUB double type, this is float type, S3, string type. So these are different types. So after that you can use it S3 dot sum, S4 dot sum, and S5. So let me, at this point, let me go ahead and make sure that I didn't have any problem, some error in this code. So I'm going to the terminal, and I'm actually running the program. So I think there is a semicolon missing at the end of the class definition somewhere. So here, semicolon. has no name. Oh, I think I should have changed this to run. This is not a sum. So let me go back to change this. This should be run. Then after that, let me have a statement to display. So going to the terminal, this is was not declared. Well, I think there's still a problem here. Let me go back again. We have should be S4. And it's not displaying anything. Well, I probably might. I probably forgot to compile again. So let me go back and take a look at the code in deep. So see out statement looks okay. This is. Let me go back and. Oh yeah, I think I noticed the problem here. When you initialize this sum is of type t, right? T can be, it can be integer, it can be float, it can be string. Particularly in this case, if it is integer, double, and float, and then 0 can be implicitly casted to that type, so it can be initialized to that corresponding 0 value. But in the case of a string, you cannot. 0 is not a default value, therefore initial value. So it should be maybe something like this, right? If I put the empty string in the beginning, then again this will not be suitable for the double type integer type. So therefore I think we can we have to initialize to default value using this syntax. This will actually see the type of this variable and set the corresponding default value to it in the beginning. So I think this should hopefully this will solve this issue, and I will be able to see the output. Let me go back and in the terminal, yeah, I can see the output here. It is working. Now here you know, this class is actually this class is a sum class is actually instantiated, or its object created, so that this object will behave differently for integer type, floating point type. Just to explain it a bit more clearly, what happens is when the compiler sees this expression, it will create a actually version of this class for integer type, like in this case, in the case of function. And when compiler sees this expression, it will create the version of that class for double type, and this will actually I mean, require the compiler to create a version of the class for floating point type, and in this case for string type. So in this case, this template class is actually I mean, showing its behavior in the different ways for different type, different value for this type parameter used. Therefore in that sense, this is also polymorphism. This is actually exhibiting polymorphism, but that actually happens at the compile time. Therefore this is called compile time polymorphism. Now I have talked about coercing polymorphism, overloading polymorphism, inclusion polymorphism, and parametric polymorphism. Thank you for watching this video.